This is a video demonstration of how to use the Clausius Clapeyron equation. I went over this example in class, but I'm correcting it in this video demonstration. So let's talk about first though what it is and why we would want to use it. The equation relates together three things: vapor pressure, temperature, and the heat of vaporization. Vapor pressure, as we've talked about, it's really just the pressure exerted by gas molecules that are kind of sitting above liquid form of the compound at a given temperature. So this is not, vapor pressure is not something that's the same regardless of the conditions. It's not something like boiling point that's always the same. It's going to differ with your temperature. And heat of vaporization is how much heat is needed to vaporize each and every last molecule of a substance in the liquid form when that sample is already at the boiling point. So the units on this are kilojoules per mole. And if we look at the equation, we see that there's a P1, P2, T1, and T2. So it's calling on two sets of pressure-temperature combos. And R in this equation is the gas constant. The units on this are joules per Kelvin per mole, and that is because we want joules to cancel out. You can see R is divided into the vapor pressure, which is a unit of joules per mole. So joules and moles cancel out just in that first little part right there. So let's talk about how we can use it. It kind of allows us to do two things. If we know the vapor pressure at two different temperatures, we can solve for the heat of vaporization. If we know the heat of vaporization in one vapor pressure temperature combo, then we can solve for an unknown vapor pressure at a different temperature. So back to that example problem. This example problem was regarding methylcyclohexane methanol, MCHM, which is the chemical that was spilled in West Virginia a few weeks ago. And it's a very relevant question. Not a lot is known about this chemical, and people were asking this question: what's my exposure if I take a shower in this contaminated water? So we want to know, what is the vapor pressure of the compound at typical showering temperature, 90 degrees Celsius. A couple other things we know about this chemical. We know the boiling point of it, and it's kind of a sneaky way of figuring out a vapor pressure temperature combo, because at the boiling point for any compound, the vapor pressure is equal to atmospheric pressure. So our first P1 and T1, the pressure at 202 degrees Celsius is going to be 760 millimeters of mercury, which is equal to 1 atmosphere. The enthalpy of vaporization, the heat of vaporization, is not known for this chemical, but a very similar chemical has an enthalpy of vaporization of 61 kilojoules per mole, so we're going to roll with that. All right, so just to summarize some of those things we gleaned from the question in this example into a nice organized list. We've got our T1 and P1 listed first, 202 degrees Celsius, 760 millimeters of mercury. But one important thing, whenever you're comparing temperatures, whether it's Charles's law or the Clausius Clapeyron example, the temperature needs to be in Kelvin. So 202 degrees Celsius is equal to 475 Kelvin. We also know the gas constant. We are using the enthalpy of vaporization from the similar chemical. And another important thing is that the units on R are in joules. The units of heat of vaporizations are usually kilojoules per mole, so we're going to need to convert that to joules per mole. So 61 becomes 61,000 kilojoules per mole. Joules per mole. And lastly, the T2, the temperature that we're trying to learn more about, is equal to 90 degrees C or 363 Kelvin. So we're searching for P2. We've got everything else in this equation. So now, how to use this equation? Let's talk a little bit about that. It's a little scary looking. It's got a natural log in it. But I want you guys to think back to kind of what you know about logarithms. Oops, there's my pen up there. So the base form of a logarithm expression you can say that the log of a number, you can solve for the log of a number. And so the log of 100, because logs are usually base 10, the answer to this is what you have to raise 10 to, which power you have to raise 10 to get to 100. So if I raise 10 to the second power, I get 100. And that's kind of the form of this logarithm. So basically what we're going to do is we have all of this information here. We have all the temperatures, the vapor, enthalpy of vaporization, and R. We can perform this calculation first and just get a number. And then when we have a natural log, it's a log with a base of e. So basically what we're going to do is kind of rearrange it and say, well, e to the power of whatever this comes out to is equal to p1 over p2. So yeah, when I'm just doing kind of normal logarithms, this can rearrange to 10 squared equals 100. And so we're going to rearrange this logarithmic expression in the same way. So let's go ahead and plug in all of our numbers. We've got the natural log of 760 millimeters of mercury over P2. That is really messy, sorry about that. And that's equal to 61,000 joules per mole over our gas constant, 8.314 joules per mole Kelvin. So you can see how joules per mole is going to cancel out with joules per mole, but we'll do all the canceling in a little bit. And so that's going to be multiplied by this temperature expression here. We've got 475 minus 363, and that's going to be over 475 times 363. And I'm not writing Kelvin in here to save a little bit of space, but let's think about what the units are on this part of it. When we subtract Kelvin minus Kelvin, we have Kelvin on the top. When we multiply Kelvin times Kelvin, we have Kelvin squared on the bottom. So one of those Kelvins will cancel out. The units on this thing, once we do that math, will be 1 over Kelvin. So doing out that math right there, if we do 61,000 divided by 8.314 times 475 minus 363 in parentheses divided by the product of those two, we're going to end up with 4.766. So make sure you have parentheses on this in your calculator, on that subtraction right there, and then you should be good to go. The units, yeah, we said joules per mole is going to cancel out. The kelvins are going to cancel out too, because since this kelvin is on kind of the bottom of the fraction bar, it's essentially on the top, so kelvins will cancel out. And so we're left with the natural log of 760 over P2 is equal to 4.76. So yeah, now we're going to rearrange this expression just in the same way I rearrange this simple log base 10 of 100 equals 2. We're going to say that E to the 4.766 is equal to 760 over P2. And now I can also, E is just a number, it's an exponential. If you do it out on your calculator, what is it actually equal to? E to the first power is equal to 2.718. So E is just a number. So you raise 2.718 to the power of 4.766 and you get 117.44. And that's equal to 760 over P2. And now it's essentially just cross multiplying. Multiply both sides of this by P2, and it'll cancel out the P2 on the right. And so we then just have 760 divided by 117.44 equals P2. So if you do that on your calculator, you should end up with P2 equals 6.47 millimeters of mercury. So that's a wrap. That's a kind of quick description of how to use this equation. The only thing you kind of need to remember from your math class is sort of how to rearrange that exponential. And so taking an example like this, just doing a simple log base 10 of 100 equals 2, and thinking about how that would rearrange is a good way to remember how to rearrange a scarier looking exponential. That ends up being not too scary because all these numbers just kind of, you plug them in, you do the math, and then they just become kind of normal numbers.